A novel approach to wildfire suppression. Forward. Climate change, whether a reality caused by CO2 or other factors, we know is real. But spending California resources reducing its own CO2 does little for California proper at the present time with respect to forest fires and their continuation. Yes, California leads the nation and maybe the world in government-supported environmental efforts. But now our own citizens are under direct threat, and no minimal decrease of California caused CO2 will stop the forest fires anytime in the near future. For anyone who is of the conviction that the forest fires will continue and worsen, the actions of fire suppression and control should be high on the list in efforts with dealing with climate change caused forest fires. The citizens should demand it. Forest fires are an extremely critical issue in many countries as well. It is accepted universally that in prevention of forest fires from happening, the foremost requirement is to spend time, money, and effort in new techniques and apparatus that would enable the success of putting out a forest fire before major destruction to both man and nature occur. This video presents a novel forest fire detection system that is based on a wireless sensor network. Once detected, a novel means is also offered to quickly address the initial phase of a forest fire through immediate fire suppression. The problem. Forest fire destruction has been a growing problem in the western states where large tracts of unreachable areas of natural forest exist. A fire that starts in an urban or suburban area, when identified, can usually be quickly handled by fire suppression personnel using ground transportation and support. The issue becomes different where a fire starts in a deeply remote area, and these ground firefighting resources cannot be used. Once such a fire has been identified and located, it can still mean many hours before any suppression can begin. In a very remote area, neither the ground suppression teams nor the air tankers can make quick action. It could be at night where tankers don't fly, and smoke may be a problem, as well as wind. Because of the remoteness, ground crews cannot quickly or at all reach the epicenter of the start. Lightning, utility wires, even spontaneous combustion can be the source of such fires. And while they start with a kindling sort of fire, with wind and dry conditions, the fire can take on an enormous proportion within a relatively short period of time, within hours sometimes. The start of a forest fire and its growth with respect to suppression can be understood by the comparison of starting a campfire. At the start of an initial campfire, the smallest kindled fire can easily be extinguished with a cup of water. When the fire is mature and burning with established heat and hot coals, 5 or 10 gallons of water may not be sufficient to put the fire out. The solution. The means to monitor these remote areas continuously during fire season and couple that with a means to quickly deliver a fire suppression response is what is needed. The mechanisms, both in size and scope, differ greatly for suppression of a starting fire versus a raging inferno that is burned unchecked for hours or days. This solution proposes a novel monitoring and fire identification method coupled with an immediate response team, unlike any approach to firefighting that has been used before. The method. First is the identification and location for fires in remote areas. Traditional methods have been eyesight using fire towers manned with personnel and binoculars. Helicopters with FLIR cameras have been also used. A later means has been the recent deployment of satellite imagery. All have their advantages and disadvantages. A series of lookout towers spread throughout areas prone to fire is unwieldy and impractical, if not impossible. Fleets of helicopters flying continuously would be expensive and dangerous in all weather conditions. Satellite technology offers a more cost-effective means, but the ability to identify a fire as it begins is difficult. That is, timing with respect to locations of satellites could be a problem, meaning that there could be too long of a lag period for a positive idea of a fire. Advanced optical sensors are currently being deployed in many countries already, including the US, Australia, Canada, Portugal, Germany, and Russia. There is a German company, IQ Firewatch, marketing this technology for a number of years. See the website and video link below for additional information. But pure optical sensing has a drawback that a clear line of sight is usually necessary. The line of sight and the early stage of the fire process problem could be solved with a second type of sensor. A new technology called Wireless Sensor Network, WSN, is now receiving more attention and has started to be applied in forest fire detection. The wireless nodes are integrated on the same printed circuit board with the sensors, the data processing, and the wireless transceiver, and they all consume power from the same source batteries. Unlike cell phones, WSNs do not require periodic recharging, provided the power drain is low and the batteries are long life. The sensors are devices capable of sensing their environment and computing data. The sensors sense physical parameters such as the temperature, pressure, humidity, as well as chemical parameters such as carbon monoxide, carbon dioxide, nitrogen dioxide. The sensors operate in a self-healing, self-organizing, wireless connected networking environment. One type of wireless technology is named Zigbee, which is a new industrial standard based on IEEE 802.15.4. This technology emphasizes low-cost battery-powered application and small solar panels being suited for low data rates and small-range communications. Wireless sensor networks have been seeing rapid developments in a large number of applications. This kind of technology has the potential to be applied almost everywhere, and especially for early forest fire detection in remote areas. In contrast with the existing conventional optical techniques for fire detection, wireless sensor networks offer greater benefits, and there are wide expectations for forest fire monitoring applications. The network can simply be placed in an area of interest or area of high risk. In the physical design of the WSN, the nodes are of two kinds: sensor node that collects the information from the environment, and the cluster nodes that gather the information of the sensor nodes and furthermore communicate this information to the base station. One can think of it as our internet now operates, to connect thousands of people simultaneously with the ability to communicate instantaneously, but just with very specific types of data. Hence its simplicity. The sensor nodes can perform different functions, which enables the creation of a self-configuring network, providing redundancy and guaranteeing full geographic coverage within an interest zone. The gathered information is not limited to only for fire detection purpose, but also could be used in monitoring the general environment conditions to increase WSN usage and cost justification. Currently, there are in-use WSN networks monitoring rainforests in certain countries. For an efficient early detection, the sensor nodes should be small, energy efficient, not very expensive, and should have capabilities that they could easily be deployed in difficult and harsh environments. In conclusion, comparing all systems possible, optical cameras and WSN stand out as the only fully operable solutions covering targeted area with completeness. Between the two, WSN is superior, offering medium cost while having high accuracy and quick detection relay of information. In addition, the WSN network could be used for other purposes. However, it is quite possible that a combination of these detection methods would be the optimum solution. Okay, we now have a system that can detect a fire starting at its initial stages. Information has been relayed to a central base station that indicates with relative high certainty that a fire has started, and the location is pinpointed to a specific remote area. Now the question becomes, how can we immediately respond as short a period of time as possible to this identified area? If we can respond quickly, the necessary fire suppression materials will be minimal compared to what we now do to combat a well-established forest fire. So this issue can be broken into two parts. One, the specific suppression material mechanism to strike the fire, and two, the means to deliver it. Werner von Braun was a German-born American aerospace engineer and space architect. While his dream as youth was space exploration, his insight and abilities were initially used for war. He was a leading figure in the development of rocket technology in Nazi Germany, and later a pioneer of rocket and space technology in the United States. Today, rocketry usage abounds in warfare. But because of all the development that has occurred, it may be time to consider the use of rocketry for a peaceful terrestrial purpose. I believe that the delivery of fire suppression material can be securely achieved by the use of rockets. Now, at first glance, the cost may appear to be high. Using rocketry to deliver fire suppression material might seem very elaborate and too expensive. But remember, we are not trying to put out a raging inferno, but a relatively small fire beginning to grow. Volumes of material are not necessary at this stage, only relative precise amounts that can be accurately and quickly delivered. The military has used rocketry, replacing most cannon and gunfire in air-to-air combat for years. Helicopters in war deliver multiple firing rocket clusters to ground targets in ground war support. These rockets are mass manufactured and are standardized design. Mass manufacture of standardized rockets capable of carrying fire suppression material would greatly reduce costs when the economy to scale considerations are taken into effect. The construction of the rockets would be as follows. The fire suppression payload would be the bulk of the rocket cargo, along with propellant sufficient to deliver the rocket to the target. It would have the means to accurately direct the rocket to the fire which is starting, and the means to detonate the rocket at the optimum height directly above the fire for maximum dispersion of fire repellent. Directing the rocket's trajectory once fired from an aircraft would be a form of heat-sensing technology perfected in the development of aerial and ground combat rocketry. Infrared honing is a passive weapon guidance system which uses the infrared IR light emission from a target to track and follow it. Missiles which use infrared seeking are often referred to as heat seekers, since infrared is radiated strongly by hot bodies. Many objects such as people, vehicle engines, aircrafts generate and emit heat, so are especially visible in the infrared wavelengths of light compared to objects in the background. And a forest fire, even at its early stage, is a strong source of infrared signal the rocket can hone in on. Infrared seekers are passive devices and are extremely effective. 90% of all United States air combat losses over the past 25 years have been caused by infrared honing missiles. The first IR devices were experimented with in World War II. During the war, German engineers were working on heat-seeking missiles but did not have the time to complete development before the war ended. Anti-aircraft IR systems began in earnest in the 1940s, but the electronics and the entire field of rocketry were so new they required considerable development before the first examples entered service in the mid-1950s. Today, they are an industry standard in warfare and require no advance in science to be put to use for fire suppression. So the next element of the rocket will be a proximity fuse to detonate a small explosive charge that would release the fire suppression material in a close proximity above the fire to achieve maximum effect. The proximity fuse came into use in World War II for anti-aircraft cannons. The fuse would explode the cannon shell when it neared the target plane so as not to actually hit the plane. This gave the destructive force of the exploding shrapnel much greater effect as destroying the aircraft. The use and design of proximity fuses is well established for over 70 years and would easily be incorporated into the fire suppression rocket mechanisms. So the final question would be the delivery of the rockets to the remote site where a fire is starting. At an approximate distance from the fire, the rocket could be launched relying on the infrared guidance to accurately reach the targeted fire. Weather conditions would decide which means of transporting the fire repellent rocketry. In calm weather, helicopters armed with multi-rocket capacities could be deployed. In unsettled weather, short-wing, high-powered, piston-driven aircraft similar to the pinnacle designs of fighter planes used in World War II might be appropriate. All-weather night fighters developed in World War II are part of technology already existing and mature. Piston engines offer quick power-up and power enough to create its own lift to overcome wind shear. These planes would have wing-mounted rockets equipped with fire suppression retardant. Another possible delivery mechanism could be drones. Armed with rockets bearing the fire retardant, they could be safely operated in inclement weather with no fear of human life loss. Or the drones could be one-use kamikaze style to be loaded with fire retardant, directed to the target fire and detonated at the appropriate height above the fire. What are the manpower requirements for this effort? During fire season, the personnel would be a 24-hour operational plan. Base station operators for the WSN networks would be on continuous monitoring operation. Base stations could be assigned to each national or state forest or subpart thereof. These stations could be connected to one central station in California and would require 24-hour operation. The other specific substations could be 24-hour call and be alerted for service when the central station receives a fire alert. The substation, in conjunction with the central station, would coordinate the choice of aerial response to the starting fire based on weather conditions and location of fire with respect to base locations of the aerial support teams. Once confirmed that a fire is indeed started in a remote area, nearby substations could be alerted for backup and assistance in coordinating the attack of fire. The next requirement to have a functional response system is the location and training of pilots for the operation of aircraft used in the delivery of the fire suppressant. Some of the planes, helicopters, and launch rockets could be stationed strategically at various military air bases located in California. Within a coordinated effort with the California Air National Guard and the U.S. Air Force, these planes and helicopters could serve a dual use. The military-trained pilots could be deployed for use in this operation, and offering training for military pilots in all weather conditions and acclimation to a 24-hour call schedule could be a real-time benefit to the military. Right now, millions of dollars a year are spent on training and grooming pilots for skills in all forms of variances in weather. In essence, this would give the military training and real operational experience in various flight conditions while at the same time serving the public good. And this would raise the public's opinion and attitude towards the vast expenditures on military readiness and the military in general. But where not practical to use military bases, stationing could occur as strategically located airports. The next step would be a feasibility study that would include the following: an investigation and verification of all the existing technology that would be needed and could be used to support this effort. This would include projected costs and dates when these elements could be manufactured and available for use. Next needed is a comprehensive report detailing where further product development is necessary, such as the fire suppressant rocketry. This report would include details regarding the estimate cost and timelines of development, along with the measure of success that could be anticipated in the final product. Third would be the completion of an in-depth inquiry to establish coordination possibilities of various government agencies that would support this effort. This might involve the establishment of various MOU agreements with establishing commitment of the various government entities that would be involved in this effort. Prototype implementation. One approach would be the independent development of the detection mechanisms or the aerial delivery systems and subsequent testing, or both parts could be developed and independently and used as soon as full deployment would be feasible. This would require two separate teams to work on one part of the proposed systems. For the development of systems for fire location and identification, prototypes could be tested in winter wet conditions with test fires. The ability to sense and to respond effectively with accuracy could be tested until final deployment would occur. The same winter testing on the rocketry could be performed for effectiveness and safety also. Funding sources: federal and state grants with cost share funding from manufacturers who would stand to benefit from the manufacture, purchase, and sale of their technologies. Insurance companies who would have an active interest in reducing their high risks they cover regarding fires. Utility companies who also suffer high losses when fires start from power line failures. The benefits of this: a reduction of large-scale firefighting personnel and equipment, if this is successful, and it could pay for itself over time. Reduction of fire losses, including the loss of human life and nature in general. Renewed appreciation of the military, their role in stopping a forest fire at its inception, could be carried by the media with stories giving recognition. And finally, California will be seen as leading the way to a solution of a worldwide problem of forest fires. Conclusions. Most of the technology mentioned in this video is either developed enough to be deployed or in need of minor modification of an existing technology for the applications described. The coordination of putting these pieces of the puzzle together is what is needed, and the cost of this effort must be weighed against the cost of wildfires. Maybe only parts of what is suggested could be used. Or maybe the whole system, when operational, could slow down and control a wildfire to give time for the tankers to completely extinguish the fire. What I'm saying here is there might be a few good ideas that could be implemented to slow the progression of forest fires that we are now experiencing in California.